Oh, yeah, sorry.
That way, but that's okay. Please.
Okay. Thank you very much for this opportunity to speak. So the talk of today would like to be a little bit of a summary of many results that involve many Hurwitz problems that are solved by topological recursion and their link with intersection and modular space of curves. So I will start by something that probably is known to many. So let me write again this Hurwitz numbers H, G, mu. So mu is a partition and G is the genus. So for me this will count some. I will be doing a lot of these strange drawings during the talk. So I will explain once what I mean by them, and then all the other ones will be the same. So I'm counting surfaces of genus G that project D to 1 to P1. Here I have my point infinity, here I have my point 0, and then here I have a certain number of mark points over here which are fixed on the base. This D to 1, and D is the, so mu is a partition of D, and here I have mu1, mu n. This is the ramification profile over 0, and in this case I want ramification profile over infinity to be trivial. And then over all these points, which you can compute by Riemann-Hurwitz formula, there should be 2G minus 2 plus the length of this partition, which is n, plus the length of this partition, which is D. And then I just have simple ramifications over all of them. Okay? And then for me the symbol will not stay for open, but instead for connected. So I want to connect the surfaces. And then this, as Melissa was mentioning earlier, this is the product of the mu I to the mu I divided by mu I factorials times integral over mgm bar. And here we have this Hodge class, and then I take the product of 1 minus mu I psi I. So I think of this as expanding them in geometric series, and this is just the alternating sum of the lambda classes. And then, okay, so this ELSV differs by the term of the automorphism, because I want, in my definition of Hurwitz numbers, I want the preimages of the ramification over 0 to be labeled. So I don't want the automorphism, but it's just a difference of convention. It doesn't matter at all. So you can define them if you want. I now define the Hurwitz numbers with this symbol. I mean possibly disconnected. And these are connected. And then you can pass from one to the other with inclusion-exclusion formula. Or if you want, just the generating series of this and the generating series of this, and one the exponent of the other. So you just take the exponent of the generating series of the connected ones, you expand them in the same variable, and then you get as coefficients the possibly disconnected ones. This is well known. And then, so for me, the definition of these guys, which are easier to define, will be just 1 over d factorial. And then I want to define the following object, C alpha. Yeah, this is in the just group algebra of SD. So very simple. I want to sum over all sigma. Sigma is in SD and is of cycle type. Is of cycle type alpha. Okay. And then I want to do the following. I take C mu, that corresponds to this partition. I take C identity, so just identity element. And here I take C2. So I want 1 for each simple ramification. So I take it to the power 2g minus 2 plus n plus d. And now I do the following. I take just an unramified point over here. I take a loop that goes around all of them. And then I put it around the sphere. And this is contractible. It's a sphere. Then gives me the identity. So I just count here how many times I get the identity out of this product. So I just have several elements of the group algebra. I expand each of these elements with the definition. Then I compute all the products, and I count how many times I get the identity. And then I divide by the relabeling of the sheets of the core. Okay? So this is my definition of Hurwitz numbers. And so I wanted to say about this ELSV formula that this was used many times to provide additional proofs of Witten conjecture after Maxim solution. For instance, Kaufman Pande, and then Mulase Tseng, and Kazarian Landau, and others, they all used ELSV formula to reprove Witten conjecture. And actually, something that topological recursion can do for us is to provide another proof of ELSV formula. So this is actually Bouchard-Marigno conjecture. It says that this actually came out of the BKMP as a framing limit where the framing goes to infinity, and says that if you take the spectral curve given by x is equal to minus z plus log z, and then y is just the identity, and your spectral curve is of genus 0, and you have the usual Bellman kernel, and you run topological recursion, then the conjecture is that you find some omega gns, you expand the omega gns, and you find the Hurwitz numbers inside. So this is Bouchard-Marigno conjecture. It was proved. Okay, so it was proved both. So in two papers. One is NR Mulase Safnouk, and the other is NR Mulase Safnouk and Borel for the matrix models. I think they're both 09, something like that. Yes. And so now I want to discuss a little bit instead the opposite of this. So how can you prove ELSV formula via topological recursion? So for me, the scheme is a little bit the following. So you have ELSV. Let me take a different color. Now you want to look at the Hurwitz numbers as functions of these parameters mu I. Okay? So then you look at this first part, and you see that this is clearly non-polynomial. This is non-polynomial in the mu i's. And this part over here, let's look at it. So I take each of these factors and I expand it in geometric series. And then I know that the dimension of this space is 3g minus 3 plus n. And each psi has degree 1, and this has degree up to g. And then, of course, this would be a polynomial in the mu i's, which goes up to 3g minus 3 plus n. So this is, in fact, polynomial. And then if you know about topological recursion, this non-polynomial part has a very precise meaning. Actually, it comes from the expansion of the xi function, right? So one thing that you can do if you have ELSV, you can extract this property of the numbers that you're looking for, saying that they are polynomial times something that is non-polynomial and is precisely the expansion of your function psi. And I will call this property quasi-polynomiality. So you can extract from ELSV the property of quasi-polynomiality. And then, so what people were doing is they combine quasi-polynomiality with cut and join equation. And then, out of this, I can prove topological recursion. And then there is a theorem that of NR, but also of Dunie-Markowski and Tam-Shadowin-Spitz with given Tal formalism that says that every time you have a spectral curve and you look at the numbers that you get out of the expansion of the omega GNs, and you find that they are integral of some class. So theorem, I would say both NR and DOS. So it says that if you take your omega gns, you can always express them as a sum of the AIs, but also the D1, Dn. And here you'll find always an integral over mgn bar of something, some class that I will call CGN. And here this will be the, this will depend on n vectors, n. And here you have product of psi classes, psi j to the power dj, j from 1 to n. And here you have total differential of minus d over dxj, dj. And you have this, the derivatives of psi functions. So general theorem of topological recursion is that your numbers will always be dealing with the intersection of the moduli space of curves.
Danny, don't you need psi AJs?
Yes, thanks. So in fact, what does prove with given tal is that you have a sort of an equivalence of this for Hurwitz theory. So for Hurwitz type of problems, whenever you are looking for counting surfaces covering P1, for instance, with a certain condition on the ramifications that can change, that can be more complicated, then every time that you have the spectral curve, you can apply this given tal formalism, and you can get integrals of some particular class that can be, for instance, cohomological field theory, and vice versa. Whenever you have a cohomological field theory, you can look for a local spectral curve on this other side. So in some cases, you have this equivalence. Given tal formalism is the following: that if you have semi-simple cohomological field theories, there is a group that is acting on them, and the action of this group is transitive. So you can always start from the trivial cohomological field theory, which is 1, and then by the action of this matrix, you can get all the other semi-simple coefficients. So for instance, in Dicton, Witten-Kontsevich, the numbers are 1 integral over mgn bar of 1 times psi 1 to the d1, psi n to the dn. So I'm intersecting all possible monomials of psi classes, just the class 1. This is a trivial cohomological field theory. And then if I apply certain matrices, but I don't have the time because given tal formalism it's long to explain. Then acting with this, whenever you have a cohomological field theory here, for instance, Hodge class over here, you can look for an element of this group, which is called given tal matrix, that gives you that. So I just wanted to say that you can prove ELSV formula with topological recursion. And if you want to do that, the only thing that you need to do left is to prove quasi-polynomiality without extracting it from ELSV, because otherwise you will get a circular argument. And what people were doing was to prove quasi-polynomiality via semi-infinite wedge. So you can express your Hurwitz numbers as vacuum expectation of some operators. So you have some operators of the, it's called Okun-Kaufman-Ripande. Operators. And then they follow some simple commutation rules. And working with these operators, you can prove basically combinatorially this quasi-polynomiality property. Then you combine it with cut and join, you prove TR, then you apply given tal formalism, and you prove ELSV.
Again, what is quasi-polynomiality?
It's the following: that your numbers that are the coefficients of your omega gns, they are they depend on certain partition, which is in this case called mu, and they are like a polynomial in this mu i's times something that is not polynomial, but this not polynomial part is exactly the expansion of this function size of topological recursion.
Polynomiality, so I can take as a definition that it's like a polynomial times this topological recursion.
Yes. So. Okay. So this was the story for the usual Hurwitz numbers. And now I would like to introduce some other Hurwitz problem. So actually, we can play the same game just by changing the conditions that we impose in this ramification, intermediate ramifications. And then we can get many other enumerative geometric problems. So this was actually one ELSV. And now I want to introduce other two enumerative geometric problems. And then discuss the relation with topological recursion and with ELSV. So they have different ELSV-type formula in the sense that they can also be expressed as integral over mgn bar of some class. Well, you will see. So,
excuse me, can you read forward the ELSV?
Oh, it's this formula. This equality over here, it's what I call ELSV formula. And it's called ELSV because of the four authors, which are Ekedal, Landau, Shapiro, Weinstein. It's 99, I think. So, okay, so I want to introduce two enumerative geometric problems. And in fact, they come from very different branches. One comes from physics. And from, so people were studying something that is called two-component Coulomb gas. And they were studying a matrix model for this that is called Herish-Chandra-Iskinson-Zuber matrix model. You define your partition function to be the integral over all unitary matrices n times n, unitary n times n. And here you have some measure and then exponent of some potential, which is just trace of u a u minus 1 b. So you fix two matrices a and b, which are a Hermitian n times n, and then here you have, I think, big N and Z, something like that. And then you study this matrix model. And this is related to a model that explains how the Coulomb gas with two components should behave. And then there is a theorem that says that if you expand this matrix model in power sums, you get some numbers. And then these numbers have an actual geometric interpretation as Hurwitz numbers, but not of that type. They are a little bit different. They are in fact counting. You always have this partition on one of the two sides. Here you have, you can have another partition over here. So nu1, nu you have some genus. And then here you also have intermediate ramifications, and they are also simple. But there is a condition that links all of them. And the condition is the following. You have here, on the first point, right? You have labeled points over here, so you can go from left to right. And the first one swaps two sheets of the cover. You look at the label of the upper sheet, and then the next one on the right can be, its upper label can be either the same or can be increasing. So for instance, the next one can be increasing, the next one can be increasing a lot, and the next one can be increasing a lot. But you can either go on the same level or higher. Okay? This is what is called monotone Hurwitz numbers.
this monotonous from the matrix integral point of view?
Yeah, so actually it's, I don't know what the monotonicity explains about the Coulomb gas, if that's the question. But in order to solve this, use this Weingarten calculus, which gives you basically by its nature the monotonicity condition. It's inside the Weingarten formula. But I don't know the physical explanation of the monotonicity. Okay, and then so its twin actually is Grothendieck the sound enfant. So something coming from algebraic geometry. You have this.
S, since you have the S before, you have to have another S. No. Grothendieck said this one. Enfant.
I'm sorry. It's just one enfant that is doing many drawings. Does it make sense? No.
Oh, okay.
Okay, so you have. Yes. I will try to rediscover the enfant inside me and make this drawing. And there is a theorem of Betti, in fact, that tells you that if you have a projective curve, then over C, then this curve is actually defined over Q bar if and only if there exists a cover that is only ramified over 3 points, 0, 1, and infinity. So here you have some mu 1, mu n, some mu 1, mu m, and here you have some ramification intermediate eta 1, eta l. Sorry for the drawing that is half complex, half real. Sorry for that. And then I want to convince you that this guy, if you count how many you have, this is equal to 1 over d factorial. I'm trying to get the definition of this that is like this. 1 over d factorial, then I have c mu, c c eta. But I want to sum over all possible intermediate ramification. So I sum over eta. But Riemann Hurwitz tells me that there is one equation that links all the ramifications. So the length of eta actually should be equal to the degree minus 2g minus 2 plus m plus n. And then I take how many times I get the identity. Right. So I fix left and right and then sum over all intermediate ones. And then I want you, and then I still need a definition for this one. I want to give you a definition for this one, which looks like this. What should I do? It's a little game about the group algebra of SD. So let me define these elements, which are called Utsi Murphy elements. So JK, I define it as the permutation, the transposition 1k plus 2k plus k minus 1k. So it's very easy. This is inside QFSD, just the sum of certain transposition. Okay? And then, so actually, if you look at all these elements, they span maximal commutative subalgebra of the center, but no, not of the center, sorry. But if you want them to lie in the center, then you have to consider symmetric functions. Symmetric functions in Utsi-Murphy elements, then they belong to the center. In fact, there is a theorem of Utsi that says the following. If you take the elementary symmetric, this is elementary symmetric, K evaluated in Utsi2, Utsi3, blah, 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 Utsi-D, and we are in the algebra of SD, and this is equal to sum of C eta with the length of eta equal to d minus k. So you have a symmetric polynomial. Now you evaluate it in some variables, but now you substitute these variables to be equal to these elements in the group algebra. Then you take all the possible, you expand all the products, and then you check that you get something like that.
What is C eta?
Oh, it was written here. I'll write it again. C eta is equal to the sum of all the gammas, such that gamma has cycle type eta. Let me make the very easy example.
Is k a degree of this polynomial?
Yes, this is the homogeneous degree. Let me test this for k equal to 1. What happens? So I have sigma 1 of J2 up to JD. Well, the symmetric elementary 1 is just the sum of all of them. So this is just J2 plus JD. But now I look at the definition of my Murphy element. It's clear that if I sum all of them, then I get exactly all the transpositions. This is sum of all transpositions. Right? But this is also equal to the sum of all the C eta with length of eta equal to d minus 1. Because whenever I have a transposition, I write it as two elements in the same cycle, and then all the other elements are alone, and the length of this is d minus 1. And these are exactly all the elements of length d minus 1. Okay, so we just verified UC correspondence for k equal to 1. And so I want to convince you now that this problem over here, you can just take this intermediate ramification, right? And now you apply Murphy correspondence with k equal to g minus 2 plus n plus n. And you get that this count over here is just equal to mu1, mu n. And here you have mu1, mu n. And here you have something that is given by sigma k of Murphy, where k is to g minus 2 plus n plus n. And so let's have a look. We know how the elementary symmetric polynomials behave. They are the sum of all possible monomials such that the index is monotone, strictly increasing. So what I will get, in fact, is a ramification, because it corresponds to a transposition. So I should have two sheets that swap. And the next one is a bit higher, but strictly higher. And then strictly higher, strictly higher. So this is what is called strictly monotone Hurwitz numbers. And it's really a combinatorial identity of the level of the blocks of ramifications. So if you take Bousquet-Melouche-Schaeffer numbers that have a lot of this, you can just replace each of them singularly with a block of ramification of strictly monotone type. And now if I want a definition for this will be equal to 1 over d factorial. I have to take how many times I get the identity inside C nu. And here I want a different polynomial. I want age, which is complete homogeneous. Evaluate, so to g minus 2 plus m plus n. Evaluated in UC2, UCD. Why is that? I know, what's the definition of complete homogeneous? If I take the generating series of complete homogeneous with some dummy variable u, this is just the product of 1 over 1 minus x I. Sorry, this is a vector of variables. Yeah. This is u. So I get all the possible monomials of variables with the index that is monotone increasing. If I have the generating series instead for these guys, this is just product of 1 plus uxi. And then from the generating series, you see that these two problems are very similar to each other. They are twins. Because their generating series somehow is, okay, one the inverse of the other if you change the sign to the variable of the generating series. And so many of the results that hold for one problem, they hold for the other.
So what's the analog of the one?
I have no idea. Like the fact that its origin as Göttingen son enfant translated in the physics meaning. I have no idea, sorry. They just have two different historical origins that in fact they turn out to be just two bases of symmetric functions evaluated in this particular element of the group algebra. And so topological recursion is known for both, and the ELSV formula as well. So this is 2.1 STR for a monotone. Okay, so actually, so let me take x equal to z1 minus z to the r, and then y equal to zr minus 1, 1 minus z to the r, and here I want to put them in the same order. So this would be strictly monotone. And this is yeah, just usual monotone. So this R parameter is, I'm imposing that the partition nu, which is the one on the right. I want this partition to be just of the form R, R, R. And the degree should be divisible by R. Otherwise, everything vanishes. So this is called the orbifold version of both problems, when you impose one ramification to be this type over here. So this one was proved by Dodd, Dyer, and Matthews for R equal to 1. And then it was conjectured by Doe and Karev for arbitrary R. And then was proved by Kramer, Popolitov, and Shadowin this year for arbitrary R. So they just proved, they proved the conjecture of Dokarev for arbitrary R. And then, this one was proved by Dumitrescu, Mulas, Safnouk, and Sorkin for R equal to 1. It's just, and then it was conjectured by Don Manescu for arbitrary R, and it was again proved for arbitrary R by Duni, Berkowski, Antan, Popolitov, and Shadowin, 2015. And the double version of those sort of open in the sense. Okay, we have. Okay, maybe I will speak about it later. So somehow, what I wanted to say until here is that we can embed the theory of symmetric functions, because these are two different bases for symmetric functions, inside like Hurwitz. We can make enumerative geometry in Hurwitz theory, and then we can look at topological recursion, and then we can look at ELSV formula. Now comes the algebraic geometry part. So for monotone, we have that, again, we have here mu, and here we have the one which is just monotone. The enumeration of these guys is equal to 2 mu I over mu I factorial, and here I have just an integral over mgm bar of something that is just exponent of kappa classes. So I just have exponent of AL kappa class L from 1 to infinity. And then here I have some non-polynomial part. So I have product of dj from 0 to infinity, psi j to the dj. And here I have 2 mu j plus dj plus 1 double factorial divided by 2 mu j plus 1 double factorial. So this is a polynomial in mu j, in fact, of degree dj. Right? And this is the non-polynomial part. And in fact, this non-polynomial part, if you look at this spectral curve over here for r equal to 1, and you compute the size, is exactly the expansion. And this was together with Alexandrov and Chardin. And then strictly monotone. So strictly monotone turned out to be much harder, actually. So this is just an application of an out formula or a DOS formula. So it's a simple exercise. If you understand the formalism, you just compute. And I have to give a generating series for this, of course. So exponent of this guy is equal to 2k plus 1 double factorial uk. And then this one turned out to be much harder. Even just applying the same math as the computation, it's quite hard.
What makes it more difficult? I mean, these two problems look very similar.
Yeah, I agree with you. Like, you think they're dual, but in fact, the computation of the size, and it's just much harder. You have to compute some residues, and you can try to compute these residues. You don't get a compact formula out of that. It's not so easy. But if you have a good formula, I would be interested. So, but however, Baron and Elba, still managed to get a formula, but in a different way. And it's not for all the strictly monotone. It's just in the case these parts over here are even. Sorry, even. So if here I put now 2 mu 1, 2 mu 2, 2 mu n, then you get beautiful ELSV formula. Here you also want 2, 2, 2, so it's for 2 orbifold. This is equal to, again, 2 mu I over mu I binomial. You have some other mu I over here and 2 to the g, it doesn't matter. And then integral over mg n bar of triple Hodge. So this is Baron and Yosefeld. I think it's 2015, 16, 17. Okay, then you have some exponent of kappa classes minus L K L over L, and then times. Here you have some g h goes from 0 to floor of g over 2, and then here you have some prefactor 2 to the minus 3h divided by 2h factorial, and then you have a Poincare dual of the following graph. So you have Poincare dual on the following graph, where here you have 2 edge points which collide. So this is age. This is genus age that is subtracted. So you can think of, in fact, just m g minus age. Here you have n plus 2h. You embed it inside mgn just by taking pairs of points and then touch them together.
Then you go to the cohomology.
Yes, yes, yes. So you just use the Glue map h times. And then you sum over all possibilities, and you also weight it with this prefactor, and you get what some people call the crocodile class or the alligator class. But you know, in Miami you have this particular situation that crocodiles and alligators live together, so maybe it should be a superposition of the two. I don't know. Okay. And then, so now we're at chapter 3. Generalized Zwanking conjecture. So now you want to, your enumerative problem now is like that. You have mu1, mu(n) as usual. Here you have some orbifold profile, Q, 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 Q. And here in the middle you have some genus. And your ramifications here are what is called completed cycles. So there are some algebraic elements. I can write down the first ones if you want, but the definition it's a little bit long. But somehow you can think of them as the following. So you have R+1 sheets of the cover that come together, plus a tail of other ramifications with certain coefficients that come from the function 1 over hyperbolic sine. And these completed cycles are important, and that tail of coefficients, exactly those coefficients are important because they are the central element, the key element in the Gromov-Witt and Hurwitz correspondence by Okonkov and Pandavipande. So Gromov-Witt and Hurwitz correspondence, really, like when you compute the correlators in moduli space of stable maps, then what you find in the Hurwitz theory that is corresponding is this completed cycle. So if you want CR completed, R minus 1 factorial is equal to CR plus a certain tail, like a particular tail of elements like that, but of lower order. So this one belongs to SR, and then the other ones will belong to R prime, with R primes smaller than R, with some multiplied by some rational numbers. So the conjecture is that this is equal to R to the 2G minus 2 plus N. Let me do it in a simpler way. There is some prefactor that is very easy, and it's just some function of some power of R and some powers of Q, which are very long to write, but it doesn't matter. Then you have product. It's just confusing and long, so I want to avoid it. You have mu I to the mu I floor. When I write this floor, I mean Euclidean division with respect to RQ. So mu I is equal to mu I times RQ plus mu I. So this is just a reminder, and this is what you get out of the Euclidean division.
Oh, I see.
So mu I factorial. Of course, if you plug R equal to 1 and Q equal to 1, this is mu I and this is mu I, you recover the usual ELSV. Okay, and here I want to integrate over NGN. Here I have a product of 1 minus mu I QR psi I. And here I have the Kyoto class Gn of QR Q. And as the parameters I have QR minus the reminders of the division. This is a vector of length n. Okay, if I have time, I will write down the definition of Kyoto classes. But okay, so for instance, you all know at least this one example of Kyoto classes. If you specialize all the parameters to 1, then you have the Hodge class. Okay, so let me erase something. So for R equal to 1, this is a Zwanking conjecture. Q is equal to 1. Thanks. I wrote it correctly in the notes, and then this is 2006, and I think it was never published. It was never even on the archive, that's what I mean. And for R equal to 1, this is the Johnson-Pandavipande-Tseng ELSV formula. It's a little bit specialized. Johnson-Pandavipande-Tseng is a little bit more general than that. And then this conjecture is solved after 5 papers. but they were not all on solving the conjecture actually. So they were like, well, they were, but they weren't. So actually, I will just briefly say what people did. This is by Shadowin, Spitz, Zwoński in 13. They just proved that topological recursion is equivalent to ELSV by a given Tal formalism. So what we said before, for this particular case, just for the non-null before case. So R is the difficult parameter, Q is the easy parameter. So it's not a big generalization from here to R. And then the spectral curve for this should be x of z is equal to z to the exponent of minus z to the QR, and y is z to the q. So for q equal to 1, they proved that Zwoński conjecture is true if and only if this ELSV, with this spectral curve gives you these numbers for q equal to 1. Then in the second paper with myself and Popolitov, Shadowin, and Zwoński, I think this is 15, we proved that the orbifold problem and the completed cycles problem, they belong to the same family, and in fact they are indexed by Kyoto classes. So they're indexed by Kyoto classes. So actually, Zwoński conjecture was not. Johnson-Panay-Panay-Tseng ELSV did not contain Kyoto classes. It was on a different moduli space. So we show that there is a continuous. There is a family of spectral curves that depend on certain parameters, this Q and R, and so if you specialize them Q equal to 1 or R equal to 1, you get both problems. Okay, then there is a paper with Kramer and Popolitov and Shadowin, I think this is 17, in which we proved the quasi-polynomiality for arbitrary R and Q. And this is like the kind of tough combinatorial part. There's really a lot of just computations. There's nothing like really deep going on, but you just need to put your hands in the computation, in the mud where the crocodile is. And then there is another paper with Barreau, Kramer, Popolitov, and Shadowin, in which we proved this conjecture for genus 0 and for R equal to 2, which is the first non-trivial NEQ. Is the first non-trivial completed cycle. And then there's the last paper of this year with Dunin, Belkowski, Kramer, Popolitov, and Shadowin, in which they just give the complete proof, any R. Okay. Do you have questions about this?
What's the geometric meaning of this formula?
So we know that there is a relation between these two parameters that give a cohomological field theory. Like in fact, so for all these parameters, it's a co-FT. So if you want, you can express also the Gormov-Witten theory of P1 when all the taus have the same index. You can express them as integrals of Kyoto classes.
Like the lambda minus 1 was
yes.
You can just do this for
Yes. Except that if you specialize for this, you know that you have 1 minus lambda 1 and so on until lambda g, whereas this Kyoto class does not vanish, it continues and gets stopped only by the dimension of Hamilton boundaries. number 4 is double Hurwitz numbers. So I want to define double Hurwitz numbers connected. G mu is the following. Just count of everything, mu1, mu(n). And here I have some nu1, nu(n), and I want to associate some variables. So to this, for instance, I want to associate a variable q, nu1. And here you have only simple ramifications. So this is the possibly disconnected equivalent is defined to be 1 over d factorial coefficient of the identity into c mu, c2. And here you have sum of all the c eta with q eta 1, sorry, q nu1, q nu length of nu. All the nu that have the same partition. So they're just polynomials in nu, and then you might want some other dummy variable here and divide by factorial, just for automorphism reasons. And then, in fact, like so far, the second ramification is kind of hard to deal with. You either consider it trivial or orbifold. But if you want to deal with double Hurwitz numbers, you have some technical problems. So there is a conjecture by Do and Karev that says that this spectral curve should be log z minus s times qz, y equal to qz, where qz is just the polynomial qi, zi, I from 1 to big D. You just fix a big D, and then you want to allow this big D to be as big as you, like bigger than all the ui's. And then they also proved that the conjecture is equivalent to quasi-polynomiality.
So their conjecture was that this satisfies topological recursion with respect to this spectral curve?
Yes, exactly. Run topological recursion with this curve, look at the coefficients, you get these numbers. And they also prove quasi-polynomiality is the only missing ingredient. So we thought, but we have experience in proving quasi-polynomiality, let's just do it. And it took us a little bit, but the paper was supposed to be on the archive today, but it was put on hold. So I don't know if it will appear tonight after 8 or it will stay on hold for several days. Never happened before. So it's apparently a suspicious paper. Okay, but quasi-polynomiality, I would say, kind of, let me write today-ish. Yes, with Borot and Do, Karev, and Elena Moskovsky. Okay, and what is the nice thing about it? Well, first of all, there is a general formula that you might know is due to Alexandrov, Chapuis, and Harnad. That is, so it's a beautiful formula that is supposed to provide spectral curves for many, many Hurwitz problems. Okay. Somehow, they prove this formula only for quite restrictive condition on the spectral curve, and in fact, this spectral curve is predicted by AC. Oh. But it falls outside of their conditions because it's not polynomial. And so this confirms AC in this case. Yeah. So in fact, let me write this because I think it's nice. AC kind of potential. So in the sense that what it can do, not physical potential, is it's strictly bigger than the cases for which it is proved for. So proved cases. So we really know many problems for which. Yeah. So if you look at monotone. So you know that even the usual monotone Hurwitz numbers falls outside of the hypothesis of AC because it's not polynomial. It's 1 over 1 plus z. It is not polynomial. Or minus, sorry. So, but you could do, for instance, 1 minus z, which corresponds to this strictly monotone. That you can do. But again, because they also assume simplicity of the poles, you cannot do this, for instance. Because so you cannot compose blocks. This would be equivalent to the Bousquet-Melou-Scheffer numbers. So this also falls outside of the hypothesis. But if you put like some QIs instead, and so you keep track of which block, so you keep them separated with a dummy variable, then yes, then you can say in a certain region the poles are simple and you can use AC. But somehow, yes, so there is some. But so it seems that it holds for many cases, but it's difficult to prove. And also here all Hurwitz problems. Because, for instance, for a spin, it gives the right curve in the leading order, but then has a tail. So I wanted to say that out of this conjecture, we also get a ELSV formula, which I will not write because I don't have time. But we get the ELSV formula, and the way we get the ELSV formula, I think it's more interesting to understand so the principle than writing the actual formulas, which is not the main point. So ELSV or double Hurwitz. It's obtained by deforming the ELSV for orbifold Hurwitz numbers.
Deform.
Yes. So you see that here, if you take QD equal to 1 and QI, all the other QI is equal to 0, you get orbifold.
I see.
And then Bertrand this morning explained that if you have a spectral that depends on some parameter, then you can differentiate with respect to that parameter. And then we differentiate the ELSV formula for orbifold for its numbers. And we get ELSV for double.
I see.
Yes. But this is just some power series in QD. But you know a priori, you know already that from the definition that it's a polynomial in the QT. You know that it's polynomial in QT. And then you impose that all the integrals over MGM bar of Kyoto class that corresponds to 1 minus mu I and so on. You have some parameters. This should be equal to 0 whenever this term is linked to something that, for instance, 1 over QD, to some power that is positive, right? Then this number should vanish, because otherwise it's not polynomial. And then you get a vanishing condition for Kyoto classes, which is non-trivial. So we get the results in intersection theory, just from topological recursion. Then if you can mention the last thing. I'd like to mention a work in progress with Do about Golden-Jackson-Vakil. Conjecture. So Golden-Jackson-Vakil, they, in fact, in 2003, I think, they conjectured an ELSV formula for these numbers over here. So you have all the, you have total ramification, and here you have mu1, mu_n, and some genus and simple ramifications. And then, so first of all, they know that this should be, this number here is a polynomial in the parts, mu i's. So you don't have this quasi-polynomiality. It's completely polynomial. It does not have the non-polynomial part. And so they say it's equal to okay, D integral over some space, so they conjecture that exists some space, x, g, n bar, and some equivalent of the lambda classes, and some equivalent of the psi classes. Yeah, this acts sort of as a Picard. And the dimension is expected to be 4g minus 2 plus n. Minus 2, yes. Correct? So what they know is that this is polynomial in the mui's. And then they know that, so therefore there is like no non-polynomial part. So this expansion from the topological recursion should not be there. And then for genus 0, they find that this space is M0n. And for genus 1, they find that this space is M1 n plus 1. Yes. And so the reason why they, well, this is my interpretation, maybe wrong, but so why they propose the space of this dimension is that they really see that the degree of the polynomial is this minus, plus 1. So therefore, the dimension of the space suggests something about the degree of the polynomial. However, we find some ELSV formula that is maybe not what they want, but we have one formula, and we find that many powers of D, actually, many powers of the polynomial in the mui's, they come from D. So D, you can see it as mu1 plus mu n. So if you have D to the big power, this is this to the big power, and then you just expand it, you find degree of the polynomial coming from a combinatorial term instead of the dimension of the space. Yes, I will finish. So one thing that you can do is you take a Johnson-Panay-Pandit-Senk formula, you specialize it like before, and then you express it in Kyoto classes, and then you put the orbifold parameter equal to the degree. So think that you have something that is R. Now you impose that R is equal to D, and therefore you only have one. Right? So you can get some ELSV formula out of the Johnson-Panay-Pandit-Senk, and if you look at the non-polynomial part of this, you have this product. Now this is equal to 0, because all the mui's, in fact, if you run the division, like D is much bigger, and therefore you lose this factor. Everything is equal to 1. But we still have problems showing that this is completely polynomial, because you have something that depends on the Kyoto class, and polynomiality in the parameters of the Kyoto class is hard to manage. And then you can get some, as an application, you can get some relations between integrals of Kyoto class just by swapping the ramifications over 0 over infinity. Okay, thanks for the attention.
Quick questions. Okay, so you can just discuss with him after. Let's go. So much, and let's thank our speaker again.